All right, next we have Karen Alves de Mata from the University of Massachusetts at Dartmouth.
All right, so hi everyone. My name is Karen, and my talk today is on quantitative reliability and resilience assessment of a machine learning algorithm. Machine learning is widely used nowadays, and we don't even need to talk about that, but especially like in safety critical systems, when these models are incorporated, they face like dynamic changing and actively hostile conditions that might lead these systems to failures and degrade their performance as well. And these systems, especially because they are safety critical systems, they must be reliable and resilient. There is no much room for failure. So many studies propose techniques to improve the robustness of machine learning algorithms, but very few consider like quantitative techniques to assess the reliability and resilience of these models under likely stress and attack scenarios. So that's where my this work comes forward. We demonstrate how to collect data during training and testing of machine learning algorithms suitable for the application of software reliability models with and without covariates, and also resilience models that Priscilla explained a little bit before today. This approach enables quantitative assessment of machine learning reliability and resilience during testing and also field operations to ensure systems operate dependably under critical conditions. So for the illustrations here, we consider a convolution neural network, which is widely used for image classification and object recognition. It's pretty much just we input an image and we're going to classify, the output of the model will be the probability of the image being from a class. And there are many types of attacks, especially generative adversarial attacks available in the literature. Here we consider two types, FGSM and PDD, and they perform quite similar. They receive an original image as input, and they inject like some sort of noise to the image and create an image that for human eye, it looks exactly the same, but for the image classification algorithms is totally different. Here we have an example of UAV that we inject some sort of perturbation, and then for the algorithm now it looks like a bird. So we also consider one defensive measure that is it's well known as well. It's called adapted adversarial training, in which we retrain the model every time that new data becomes available. And we also include adversarial attacks in the training, so the model can also learn what an attack is and what it should ignore and not consider as a real image. For reliability and resilience models, reliability models use failure data to predict when the next failure is going to happen or how many failures we're going to have on the next time step. Here are all the models that I consider, but there are many open source tools available as well, in which you can just plug in your data and analyze the results of the models. Here we have with and without covariates. Covariates are the testing activities or any factor related to the system or to the failures that you are considering for the problem. For the resilience models, I consider it three types. And resilience, we are trying to predict when the system is going to come back to a high level of performance after some sort of failure. And there are more models as well, and we hope to release an open source tool very soon about these ones as well. So for the data collection process, as I said, we consider a CNN model, and we start by pre-training this model with just real data, just clean data, no attacks at all. And then we pre-train this model until it reaches a high level of performance that we consider is like ready for deployment. Once it is ready, we create a new data set that we call poison data set with real images and fake images, which they are created by the two methods that I mentioned before. And then we mix these two types of data to evaluate how this model performs on that data. And then we collect several factors such as failure time, failure count. Failure here we consider every time that the model does not classify an attack as an attack, and it classifies as a real image. Epsilon here represents the amount of noise that it was injected in the images. I consider four types of epsilon ranges because smaller epsilon ranges are harder to be detected, and higher epsilon ranges are easier to be detected. So we also wanted to identify how this would impact the reliability and resilience of the models. Once we collect this first part, we perform the adapted adversarial retraining, and then we collect information about that as well, about the accuracy and loss of the model, and also about how much memory you use, like for the retraining. And then we repeat this process several times until we have enough data for the reliability and resilience models. And then here we have some results. On the right, we have the models with covariates, and on the left, models without covariates. The models with covariates perform way better than the other models, and we were able to predict the failures on the next time step with all of the cases. And here we have on the right the frequency of covariates that were included in the software reliability model with covariates, just to identify if there was any type of covariates that we should focus our resources to collect the data. And it was not the case for this model, but it still was important to analyze that. With the plot on the right, on the left, we can see the prediction of the number of failures in the next time step. And our models as well performed quite well, and we were able to predict that easily. Here we have the reliability plot for all the cases. For the case that the epsilon range was higher, the reliability of the system goes faster to 1, which is expected since the attacks are easier to be detected on that case. In the other cases, they still go to 1, but take longer time. For the resilience models, epsilon range, the smaller epsilon range did show multiple shocks, but that's the same thing. The models were harder, the attacks were harder to be detected in those cases, so the accuracy it went up and down like multiple times because of that. We consider performance here accuracy, sorry about that. But most of the models, like in all cases, they still perform quite well and were able to track and predict the performance of the model like after some time steps as well. So as a conclusion, just we demonstrate the applicability of the quantitative reliability and resilience. Software reliability models with covariate performed way better than the models without covariate, indicating the importance of collecting these covariates and applying them on these models. Resilience models also perform quite well, incorporating these negative and positive factors as well. And for future research, we plan on exploring the application of these models to cyber-physical systems and also incorporate these models into maintenance models. And here's the acknowledgement. Thank you.
Well, thank you.